Hey everyone, and welcome. Today, we're going to break down one of the most fundamental concepts in all of physics, force. It's kind of like the invisible hand that shapes pretty much everything that moves in our universe. And in this explainer, we're going to make it visible. So, I know this sounds like the setup to a really strange joke, right? But what if I told you the answer is actually central to our topic today? You see, each one is a perfect example of how forces create motion, just on, well, vastly different scales.
To get to the bottom of our little riddle, we need to step into the world of dynamics. This is the branch of physics that's all about understanding why things move. And the answer, every single time, comes down to forces.
Okay, so here's our game plan for this lesson. We're going to start with the basics of what a force is, something you already have a feel for. Then, we'll build up to the super important idea that force is a vector. After that, we'll introduce a really powerful tool that physicists use to visualize problems, do a quick knowledge check, and then I'll leave you with something to chew on. All right, let's dive right in. The great thing about the concept of force is that you already have this built-in, intuitive idea of what it is.
I mean, think about it. Every time you open a door, kick a ball, or even just lift a bag of groceries, you're applying a force. It really just boils down to a push or a pull. And this simple, everyday experience, it's the perfect starting point for our scientific definition.
But of course, not all pushes and pulls are created equal. Just look at these two examples. The push on a cannonball is absolutely immense, right? But the pull of gravity on a tiny flea is almost nothing. This strength of a force is what we physicists call its magnitude. And as you can tell, it can vary a lot. Okay, so let's move on and see how we can build a more complete and honestly a more useful definition. Because it turns out it's not just about how hard you push, but also which way you're pushing.
So here's the crucial point. To really define a force properly, you need two key pieces of information. You need its magnitude, that's the how strong is it part, and you need its direction, the which way is it going part. A push to the left is completely different from a push down, right?
And because a force has both magnitude and direction, physicists classify it as a vector. Now, this is so incredibly important because it means we can use all the cool tools of vector math to analyze and predict motion, usually by representing forces with simple arrows.
Now, knowing that forces are vectors is one thing. But how do we actually use that fact to understand a real situation, like our ice skater from the beginning? Well, we need a way to visualize all the forces that are at play.
Before we start drawing anything, there's a key rule we have to follow. We only care about external forces, the pushes and pulls acting on our object from the outside. Think of it like this. Trying to move your car by pushing on the dashboard from the inside. You're applying a force, sure, but the car isn't going anywhere, is it? Those internal forces just cancel each other out. You need a force from the outside to actually get things moving. And the tool we use for this is called a free body diagram. It's brilliantly simple but incredibly powerful. You just represent your entire object, no matter how complicated it is, as a single dot. Then, you draw vector arrows pointing out from that dot for every single external force acting on it. Okay, enough talk. Let's actually put this into practice. We're going to build a free body diagram from scratch for our ice skater being pushed by two friends. You're going to see just how simple and useful this thing is. Okay, here we go. Step 1. We isolate the body. Our third skater becomes a simple dot. Forget the skates, the hat, all of it. They're just a dot. Step 2, we identify the external forces. So who is pushing or pulling on the skater from the outside? It's the two other skaters, right? Those are our external forces. And finally, step 3, we draw and label the forces. We draw one arrow pointing out from our dot in the direction the first friend is pushing, and a second arrow for the second friend. And that's it. We've done it. We've successfully isolated the system and visualized all the external forces acting on it. That is a complete free body diagram. All right, you've seen the concepts, you've seen an example. Let's do a quick knowledge check just to make sure everything is clicking into place. So here's a question for you. What is the main reason we use a free body diagram? Is it A, to show the internal forces inside an object, B, to illustrate all the external forces acting on an object, or C, to calculate the speed of an object? Think back to that key rule we just talked about. I'll give you a second. If you said the answer was B, to illustrate all the external forces, you are absolutely correct. Great job. Remember, a free body diagram is all about simplification. We're trying to clear away all the clutter to get a clean picture of only the outside forces that can actually change an object's motion. So we've covered a lot of ground today, from basic pushes and pulls to vectors and diagrams. To wrap things up, let's touch on one final idea that really gets to the heart of what it means to measure a force.
For a definition of force to be really scientific, we need a consistent way to measure it. We need a ruler for force, right? One classic way to do this is to use a standard, like a spring. We can decide that stretching a specific spring by, say, 1 centimeter creates 1 unit of force. Then any other force can just be measured as a multiple of that standard unit.
And this brings us to our final question for you, and it's a bit of a challenge. A spring is a pretty good standard, but it's not the only one. So my question is, what else could you use? What other physical thing produces a consistent, repeatable force that could serve as a standard for all other forces? Take some time to think about it. I'd love to see what you come up with in the comments below.